So, to review what we did in the last session, like an hour ago, we learned about the difference between complex and normal splitting. And just in case anyone wasn't there, I will super quickly recap. So, basically, splitting is when one signal is split into different peaks by other hydrogens. And we have the n+1 rule, we have the 3 bond lengths rule, and we also have the heteroatom rule. So essentially, we cannot split through a heteroatom, and a heteroatom is anything besides a hydrogen or a carbon. So an oxygen, nitrogen, sulfur, things like that. When we talk about coupling constants and J values, we have to remember that this is related to the Karplus curve. I'm not going to cover the Karplus curve, but you should look at it at least once just to kind of have an idea of what it is. And it's basically telling us the Hertz value by which hydrogens split one another. And the rule I want you guys to remember is you will have different J values if you have either different hybridizations or you have different orientations on a cyclohexane ring. And that's written here, but I'll repeat it one more time. So you will have different J values for the purposes of this class only when you have different hybridizations or when you have different positions on the ring. So for example, we said that axial and axial versus equatorial, equatorial, we are going to have different J values based on which direction the hydrogens are pointing. When we're talking about hybridization, what I mean is, for example, these carbons are both sp3, so we know that the hybridization is the same. When we go over here, we have sp3, sp2, sp2. So now it's different hybrid. I'm so sorry, but there's a phone ringing, and I don't know if you guys can hear it, but it's driving me crazy. I'm sorry if you can hear it. Anyways, so if you have different hybridizations, like in this example, we're looking at the red hydrogen. We have an sp3 carbon here, an sp2 carbon here. So you are going to have different J values, and that is complex splitting. Tree diagrams, I'm not going to go back into now. You can watch the recording. If you missed it, it's just going to take way too long. So any questions about this before we move on? Okay. Wait, can someone be my guinea pig and just unmute and say something?
Hello.
Okay, sweet. Thank you so much. Because last session it just wasn't working, and I don't know why. All right. So, first and foremost, let's answer whatever questions we didn't hear. So, we already know the formula, so I'll just fill that in for you. And the second question is a fill in the blank. So, is splitting going to happen in hydrogen NMR or in carbon NMR? What do you think? It absolutely does not happen in CNMR. So you guys are totally correct. Yay. Okay. So we are going to do one splitting example. You can do the other two on your own, and then we're going to move on. So let's do this one. Sorry, my hand is kind of shaky. So first, I want you guys to tell me what is the absolute first thing we think about when we do anything NMR related? Symmetry, cool. So do we have any symmetry? Yay or nay? Ooh, I am still tricking some people. Good, okay. So this is considered internal symmetry. So these two methyls are going to be exactly the same. So people who said yes and people who said no are both kind of right. There's no symmetry across the whole molecule, but there is internal symmetry right here. So remember that. So I'm going to go ahead and say we have 1, 2, 3, 4, 5, 6 hydrogens that are all part of the same signal. So the integration is going to be 6. So I'm going to write 6H. Next up, we have 1 hydrogen here, all by itself. Integration is 1. Then we see 2. Then we see, oopsie. Then we see 2. And then we see the lonely red one over here. Any questions on how I counted these signals? If so, let me know, but I'm going to keep talking. So altogether we have 1, 2, 3, 4, 5 hydrogen signals, and we're going to go through and do the splitting for each one. So starting with the red one, okay, so someone asked, okay, 2 people asked really great questions, so let's answer both. So someone said they get confused when whether or not the purple hydrogen is going to be there. So purple or pink, however it looks on your screen. So it's only going to be there when the carbon doesn't have 4 bonds shown. So for example, if we have this carbon right here won't have any implicit hydrogens. But if we have a carbon like this, now there's only 3 bonds, so we know that there has to be an implicit hydrogen that's not drawn here. It's the same idea when we have something like this. There's only 2 bonds, so we know that there has to be 2 implicit hydrogens present. So it always just depends on how many things are attached to the carbon. So here we had 1, 2, 3 things attached. There has to be 1 implicit one. So let me know if you want any further clarification. So are the blue hydrogens the same signal? So let's think about it, right? That was going to be my next question. When we're talking about types of signal, we have to watch out for diastereotopic, right? And so what are the 3 things we always look for when we're figuring out the types of signals? And then someone said, just to clarify, there will be a hydrogen there if there's not 4 groups present. Exactly. So if there's ever not 4 groups present on a carbon, that means there's a hydrogen. Yes, we're looking for double bonds, chiral centers, and pro-chiral centers. Cool. So do we have any chiral centers present? Yay or nay? What do we think? Nope. I agree with you. Do we have any pro-chiral centers present? Pro-chiral, yes. So potential chiral centers, we do. So I'm going to highlight those. So someone remind me what a potential chiral center is, or what are we looking for?
Two H's carbon and then 2 different groups.
Awesome, perfect, well said. So you need 2 different unique groups and then you need 2 hydrogens. So this one is a potential chiral center and this one is a potential chiral center. So this one is not a chiral center because we have 2 of the same group here. So there are 4 groups, but 2 of them are the same, so it's not chiral. So, next question, do we have any double bonds? Yes, but is that going to affect, or is this carbonyl double bond going to give us any chance of having diastereotopic. No, exactly. So when we say double bond, don't consider a carbonyl as that because that's a whole other thing. So when we're talking about diastereotopic, it has to be a carbon-carbon double bond. So you guys killed it. So the relationship between the two blue hydrogens will be what? One person said it, you're so fast. I want like one or two other people to attempt it. Enantiotopic. Yes, I 100% agree. Same thing for the green hydrogens. They are enantiotopic to one another. Cool. So, moving on. Let's start with the red hydrogen and let's do the splitting. So, let's count 3 bond lengths. 1, 2, 3. So 1, 2, 3. The only thing they can reach is the green hydrogens. And so what do we call a triplet? Oh, darn it. Whatever. It's that kind of day. All right, so now that I did the first one for you guys, I want you guys to walk me through the rest of them. So green, tell me what to write. How many neighbors does the green hydrogen have? 3, okay. So 1, 2, 3, awesome. 1, 2, 3, awesome. So we have a quartet. What about blue? How many neighbors does the blue hydrogen have? Or the blue signal, excuse me. 3, because we have 2 green ones and 1 pink one. So this is another quartet. So this pink one has how many neighbors? How many neighbors do you think the pink one has? 6, I agree. So what is it going to be called when we have 7 as our multiplicity? Oh, I'm so sorry. I said 6, but I meant 8. So we have 6 here plus the 2 blue ones, so that's 8. Yes, you guys are totally right. I apologize. I was thinking the right thing and I wrote the wrong thing. So we have the 3, 6, 7, 8. So we have 8. And so in total, that would be 9. And that would be a nonnet, aka a multiplet. I'm so sorry if I confused anyone. I forgot to add the 2. Any questions so far? All right. So this last one is yellow. How many neighbors does the yellow one have? Okay, someone said wait. I'm waiting. I shall wait. How is it 8? All right, great question. I apologize for confusing anyone. So the pink hydrogen has 1, 2, 3 bond lengths away. So all of these are neighbors. 1, 2, 3. All of these are neighbors. 1, 2, 3. Both of these are neighbors. So altogether 3, 6, 7, 8. Cool. Okay. So the yellow one has how many neighbors? 1, exactly. So we have 1 plus 1 equals 2. So this is a doublet. So I will move this over so you know it's related kind of, but also not really. And then you guys can take a picture, write it down, do whatever you would like. And then you can also ask me any questions. And I'm going to give you guys approximately a minute to do that.
Can you scroll up so we get the top part too?
Yes,
Thank you.
absolutely. You're so welcome. I am turning my camera off for just a second. I will be back in a moment. All right, so while I do this, does anyone remember what spin-spin splitting is? I believe Dr. West mentioned it briefly, and we're definitely going to talk about it, but I want to know if you guys remember. So what is spin-spin splitting? Oh, and then someone asked a question, which was, for number 2, would there be a hydrogen here? Yes, there absolutely would be. You are correct. Okay, so spin-spin splitting is essentially just saying that something is higher than a singlet, right? So anything higher than a singlet shows spin-spin splitting. So if it has 0 neighbors, it does not have spin-spin splitting. 1 or more neighbors, it does have spin-spin splitting. So let's go left to right. If we draw out this hydrogen, I am going to zoom in actually. This yellow hydrogen, how many neighbors does it have? 0, and why not? Because of the heteroatom, and because it doesn't have anything 3 carbons away. So first of all, it can't reach anything anyway, but also there's a heteroatom in there. Sweet. So the pink hydrogen, does it have any neighbors? Yes, it does. Just so I know you know, tell me how many neighbors? 2, 1, no, 6, yes. Guys, come on, I tricked you. That's okay. Don't be sad if I tricked you. I'm just being a jerk today. So I only drew one of them out, but you have to remember there's 3 hydrogens on each, so the pink one actually has 6 neighbors. And we can stop there. We don't have to do anything else because we know this has a neighbor, so automatically we know that it does in fact show spin-spin splitting. So it's as simple as that. And if it's not simple to you right now, it will be after a couple tries.
Rose,
Yes, what's up?
so when it doesn't have neighbors, it spins, or is it the other way around?
The other way around. So I'll actually like write it here as a little note for you guys. So 1 or more neighbors equals spin splitting. So yes, the question is the yellow one doesn't. So yes and no, the yellow one does not have any neighbors, but in order for a molecule to show splitting, you just need at least one signal to be higher than a singlet. So as long as one hydrogen has a neighbor, you're good. It doesn't have to be all of them. Does that make sense, kind of the way I said that? Cool. All right, perfect. So this next one, I'm going to give you guys a couple seconds to look at it on your own. Just think about it, and then I will cover it with you. But I do want you to take a look-see. Disgusting. That's my sister. I'm not just mean to random people, I promise. Okay, so what is the absolute first thing we always do for NMR?
Symmetry.
Symmetry. Yes, music to my ears. So we have symmetry down the middle right here. So how many total signals do we have in this molecule? Ooh, I got two different answers. So let's draw them out. 1, 2, 3, 4. So we have 4 different hydrogens present, but we only have one signal because there's a line of symmetry down the middle. This is exactly the same as this. So all of these hydrogens are exactly the same. It's all one signal. So if that's the case, can any of these have neighbors? No, because it can't be split by itself. So it has to be a singlet, and therefore, no, it does not have splitting. The previous example, yes, had 3 hydrogen signals. You are correct. This one only has 1 hydrogen signal. And so the last one, first of all, what's the difference between the first one and the last one? There's only one tiny little difference. There's an extra methyl, exactly. So we already know this hydrogen over here can't be split by anything because of the hetero atom, but now we have 9 hydrogens here that are all symmetrical, and there's no hydrogen here because we have 4 carbons, or 4 bonds, excuse me. So therefore, is there any splitting going on in this molecule? Nope. So the answer would be no. Awesome. You guys are doing so good. Okay. So I'll give you a second while I take a sip of my drink, and then we can move on to whatever comes after complex splitting. Okay, someone said the symmetry thing is going to kill me. I always forget it. I'm thinking of something extra to do that'll help you remember. Just, okay. Anytime you do an NMR question, just imagine me in your brain just really, really, really close, just being like, symmetry, symmetry, symmetry. And that'll stay with you forever. It'll haunt you. Trust me. Throughout the semesters, there's so many things like that where the best way to teach you is to just kind of scar you a little bit so that my voice is just in the back of your head all the time, just screaming things. That sounds so creepy when I say it like that, but that's what you get. All right. I'm going to assume we're all good with this one, so we're going to move on. We did this too. All right, my favorite question. And by that I mean I hate it with my whole heart. So this lovely word, theoretically, right? He does that to trick you. So the J value between A and B and B and C are actually going to be exactly the same because all of these carbons are sp3. But he's saying pretend they're not the same. So what is he really asking you? Pretend they're different hybridizations, exactly. And so yes, I can repeat the question. So basically it's saying theoretically JAB and JBC are different, right? So if we were to rephrase that, what question is he actually asking you? There's a couple good answers, but it's a little bit different. And to all my friends who are going to take the MCAT, this is something you should definitely start doing and start getting used to. Reading a question and figuring out what they're actually asking you and like rephrasing it in your head. So this one, he says, how many peaks would you theoretically see if the J values were different? So he's essentially telling you, like some people said, pretend it's complex splitting and tell me the answer. So we also know that he said B. Usually he'll tell you what is the splitting for hydrogen B. So we know we have hydrogen B. And complex splitting automatically means n plus 1 times n plus 1. Oopsie. N plus 1, as you guys already said. So the first n is what? So what is the first n going to be equal to? 3, okay. Are you sure? Six, exactly, because what's that magic word that I'm whispering in the back of your mind? Symmetry. Yes. So we have internal symmetry right here, right? So both of these are going to be one signal. So on the left side, we have 6 neighbors. Someone said, which one are we looking at? So that's my bad. If I thought I said, how many neighbors does it have on side A? So I meant these two. And the reason we know that there's 6 total is because, one, we could draw them in. So we know 1, 2, 3, 4, 5, 6. We know that they're all the same because of this symmetry. They have internal symmetry. And so yes, we do n plus 1 times n plus 1. So we do n plus 1 on the left side, n plus 1 on the right side. That's how I like to think about it. So on the left side, we have 6 plus 1. And on the right side, we have how many neighbors? 2. Awesome. So we do 2 plus 1. So we get 7 times 3, which gives us 21. So this is how he's going to ask you a complex a complex splitting question. And yes, so 21 is the multiplicity for specifically hydrogen B. You are correct. It would be different if we were looking for the other ones. And someone unmuted to ask a question, but then I said something. So if you have a question, please let me know.
How did you get 2?
Great question. So on carbon C, we have 2 hydrogens. And so these would be the neighbors on the other side. You're so welcome. All right. Cool. Okay. So let me zoom out, and you guys can take a picture of this question or write it down or do whatever, and then we're going to zoom through 2D NMR. I am so determined to finish this today. All right. So buckle up, kids. Okay. So these questions, he's only going to ask you like one or max two questions on 2D NMR, and you don't actually have to know any science for them. I didn't tell you that because that would be wrong, but you don't need to know anything. You just need to know my cute little tricks, right? So Cozy is telling us more information about hydrogens that are adjacent. So it's going to tell us about hydrogen. So proton to proton, yes. And so these protons are so, it doesn't look like it in this picture, but let's do it like that, right? These protons are so close together, they're nice and cozy. They're all cozy with one another. Ah, you see. There you go. Okay. So depth sounds like depth. So this is telling us in-depth information about our carbons. It's going to tell us CH4 versus CH3 versus CH2 versus CH. So it's purely telling us whether a carbon signal has 4, 3, 2, 1, or 0 hydrogens. So again, it's telling us the in-depth information about each carbon. All right, so het core is stupid. I don't have a good thing for that one. It just stands for heteronuclear correlation spectroscopy. If you just know the name, that's good enough for this one. And it's basically telling you information about different atoms' nuclei. So someone said carbon to proton. Yeah, it's telling us like the difference between a carbon and a proton or a nitrogen or a sulfur, you know. And I like to think of it like the nuclear core. It's looking at the core of the atom. I don't know. The first two are great. The last one, just know the name. And that is it. We finished another topic. Yay. So that's funny. Okay, so someone said het core sounds like Hector, and he may be hetero, so like different. That's funny. Okay. Sorry, I just thought I'd mention it. Yeah. So I'll give you guys a second to take a picture or write notes or ask any questions, but that's pretty much it for 2D NMR. Yay, we finished another topic. Could you repeat what you said about the third one? Yes, I can. So het core is just heteronuclear correlation spectroscopy, and all that means is you're essentially studying the different nuclei of different atoms. So for example, you're looking at the difference between a carbon and a hydrogen, or a carbon and an oxygen, or a hydrogen and a nitrogen. So I like to think of it as nuclear core. You're looking at the different nuclei. And then someone in the chat said it sounds like Hector, and Hector may be hetero, so he likes other people. Okay. I did talk about J values this morning. It's a lot. It takes some time, so I would recommend watching the video. You are so very welcome. I'm sorry, I don't know what that was. It just fell out of my face hole. Okay. We are on to mass spec, people. We're almost done. We got this. Okay. I'm trying to decide if I want to go through the questions like this or if I just want to draw something for you. I think I'll do a little bit of both. Okay. So, someone tell me, mass spec, what do you know about it? Teach me something. Yes, there's something called M+, awesome. Molecular weight, high energy, base peak, mass, awesome. These are all awesome things. Cool, cool. Okay, if anyone has anything else, please feel free to keep saying them. But, ooh, brom. Oh my gosh, you guys, you know so much. This is going to be easy then. All right. So, the purpose of mass spec is to tell us the mass. So, and from the mass, we can then figure out the molecular formula. So, the four things we are going to look for, you guys pretty much said it, is the base peak, the M+ peak, the M+1 peak, and the M+2 peak. And we're going to go over what each of those means in 1 second. I am just going to open a different page. So give me a moment. All right. No, I'm just going to be, no. Yeah, I'm going to be lazy. All right. I already drew this the other day for tutoring and I don't feel like drawing it all over again. So I'm just going to show you what I already drew and then we'll talk about it. Okay, so mass spec, basically you are going to take a molecule, you're going to hit it with a beam of some kind, and that the beam, like the laser beam, is going to break apart the molecule. So these pink squiggles are basically just telling us all the possible places you can break this molecule, right? And you can essentially break any bond. And once you break the bond, you're going to make a radical. And in this case, I'm showing you the most stable radical. And so in order to get the most stable radical, we are going to cut off the chlorine. And the reason is, if we cut off the chlorine, we end up with a tertiary radical. And we know that tertiary radicals are the most stable. And it's written up here just for clarification. And don't worry about allylic and benzylic yet, but we're going to talk about it in the chapters to come. So the most stable radical is the more substituted one. Any questions about the general idea of mass spec before I zoom out a little bit? No? Okay, cool. So the four main aspects are the base peak, the M+ peak, the M+1, and the M+2. And so the base peak is basically the most abundant fragment, which correlates to the most stable radical. So in this case, if we were to use that same example that we just did, this would be what is demonstrated by the base peak. And the base peak is going to be the tallest peak in the whole spectrum, and it will be very close to 100% absorbance, or 100% abundance, excuse me. The M+ peak is the parent peak, aka the molecular ion. And so that is going to tell us the mass of the unfragmented molecule, so the whole molecule. We'll talk more about that in a second, but essentially sometimes the base peak and the M plus peak can be the same, but they are not always the same. I'm just erasing some stuff so we can do it together. Okay, sorry. So the M plus 1 peak is basically telling us about the carbon, hydrogen, and nitrogen isotope percentages. And so essentially every single molecule that we're going to look at has carbons and hydrogens. Therefore, it's going to have a super tiny M plus 1 peak. And this is because there's approximately 1% of carbon-13 in nature. So there's going to be approximately 1% abundance of carbon-13 in every sample that you have. So therefore, every single compound will have a tiny M plus 1 peak. Not every molecule will have an M plus 2 peak. Only molecules that have an oxygen, a sulfur, a chlorine, and a bromine will have an M plus 2 peak. And I usually go through and I ask you guys to tell me what the percentages are, but someone had already sent them in the chat, so I left them filled in for you. There's approximately a 0.01% of oxygen and 4% of sulfur. So essentially, if you have a really, really tiny peak, it's either oxygen or sulfur, but wink, wink, nudge, nudge. If I were you, I wouldn't worry as much about oxygen and sulfur. I would just focus on chlorine and bromine. Wink, wink, nudge, nudge. So, chlorine has a 33% abundance, which is essentially saying that if we have a chlorine present, we will have an M plus 2 peak that is 1/3 the size of the M plus peak. So that's what this ratio is telling you. The M plus peak is 3 times the height of the M plus 2 peak. Bromine has a 99% ratio, so it's approximately 1:1. Or excuse me, it has a 99% abundance, which means it has a 1:1 ratio approximately. And what that means is that the M plus peak and the M plus 2 peak are essentially going to be the same height or close to the same height. I also want to give you one tidbit of information. So bromine, what it means to have a 1:1 ratio is that there are 2 isotopes of bromine that are found in equal abundance in nature. So does anyone know what the mass on the periodic table is for bromine? Y'all? Okay, you gave me the answer to my next question, which is cool and all, but like, stop stealing my thunder. Just kidding. So the periodic table says that bromine has a mass of 80. And as you guys said in the chat, that is an average of the 2 isotopes. So the actual masses, the actual masses of the 2 isotopes are 78 and, 79 and 81, and that averages out to an 80 mass. So he could ask you a question about the mass of bromine. Just know that the mass of bromine is not 80. It's 79 or 81. Random tiny tidbit of information. But we did just talk about a lot, so I'll zoom out a little bit. Any questions, comments, or concerns so far? Also, I am absolutely completely just joking when I get upset at you guys for answering like the questions and getting ahead. That's a joke. I love when you do that. We know. Okay, good. I don't know. Sometimes people really don't understand my sarcasm, and I feel bad offending people. Okay. Anywho's. Yes, I can definitely explain the bromine thing again. Okay. So, bromine has two isotopes that are equally abundant in nature. And so those two isotopes have a mass of 79 and a mass of 81. And so on the periodic table, it says the mass of bromine is 80, but that's just an average of the two isotopes. So if he were to ask you a question about what is the mass of the most abundant isotope of bromine, it's not 80. It's 79 and 81. And those two are found in equal abundance, pretty much. And then someone said, so mostly oxygen, sulfur, chlorine, and bromine have an N+2 peak. Yeah, so for the purposes of this class, only oxygen, sulfur, chlorine, and bromine have an N+2 peak. Nothing else will have an N+2 peak. And someone asked, will there be other isotopes we need to know? Not specifically, no, I don't think so. So, we're going to do an example together. The mass of this boy is 92. And so we know that if we cut off the chlorine, we make our most stable radical. And so we do 92 minus 35, and we get 57. 57 is the mass of the most stable radical. Oh, someone asked a question. What about chlorine? As long as you know the ratio for chlorine, that's all that matters. Okay. So we know the mass of the... Okay, so someone asked where I got 92 and 35 from. So I just added up the mass. So the mass of chlorine is 35, the mass of each carbon is 12, and the mass of each hydrogen is 1. So if you add all those things together, you get 92. And then if you take 92 and you subtract the mass of chlorine, you end up with 57. And so that is the mass of the most stable fragment. So, yes, I can repeat that. So we are basically going to go through and like make the most important parts of the spectrum here so we can figure out like what everything is. And we know that the M+ peak is the mass of the entire molecule. So if we're doing this example, we're going to go through and add up the mass. And so chlorine has a mass of 35. Yeah, I can just write out how I got it. So the mass would be carbon is 12. So 12 times 4, because we have 4 carbons, plus the mass of hydrogen is 1 times 369 plus 35, which is the mass of chlorine. So altogether, that equals 92, and that is the mass of the molecule. Does that make a little bit more sense? Yes? Okay, sweet. So, I forgot exactly what I was saying, but it was something along the lines of, we know the M+ peak is the mass of the whole thing. So we know that the M+ peak is going to be at 92 because that is the full mass. So let's go ahead and draw a peak at 92. and we said that will be M plus. Remember, this here is the mass over charge, and the charge is 1. So basically, this is the mass, the x-axis. And the y-axis is going to be the percent abundance. All right, so once we have that, we know that the base peak is going to be 100% abundance, and we know that it represents the most stable fragment. We know that this is the most stable fragment, and the mass of this is 57. So at the point 57, we're going to have a really, really tall peak. Ta-da! And that is the base peak. Now the ones that are a little bit easier is M plus 1 and M plus 2. So we know that M plus 1 is telling us about carbon, hydrogen, nitrogen. And I told you that it's always going to be a teeny tiny little peak. So we know that it will be teeny tiny. But what some people have difficulty figuring out is where that goes. So when you see M plus 1, plus 2, minus 10, minus whatever, we're going to start at M plus and going this direction is minus, going this direction is plus. So M plus 1 just means 1 unit to the right. So we get our teeny tiny M plus 1. So what number do you think M plus 2 will be at? $94, exactly. So let me pick a different color. All right, so M plus 2 will be at 94. And we have a chlorine present. So how tall is the M plus 2 peak going to be? 1/3 the height, exactly. So it's approximately going to be that tall. So someone is asking why we subtracted the mass of chlorine from 92. So the base peak is telling us the most stable fragment. And so we know this is the most stable fragment. And so we take the total mass and we subtract by the mass of chlorine because the chlorine is gone, and we get 57. So that's why we subtracted chlorine. You're so welcome. All right. So that is essentially all there is to mass spec. I included another example down here where the base peak and the M plus peak are the same. So anytime the M plus peak is the one at 100% abundance, we know that that is also serving as the base peak. And someone said, how do we get M plus 2 and what does 1/3 mean? So basically, M plus 2 is going to only be present if we have oxygen, sulfur, chlorine, or bromine. We have chlorine, so we know it's there. And then we know that it's going to be 1/3 the height of the M plus peak because of science stuff, but at this point, just know because I told you so. So chlorine is 33% of the M plus peak, so it's going to be 1/3 the height of the M plus peak. That's what these ratios stand for. All All right. So the last thing I'm going to mention is we kind of didn't really talk about nitrogen, right? Because when I say this, people get confused. So I save it to the end. So nitrogen is technically under the M+1 peak, but the M+1 peak is always going to be tiny, always. So when we want to find out if we have a nitrogen, we're not going to use the M+1 peak. We're actually going to use the M+. If the total mass of a molecule is odd, we are going to have an odd number of nitrogens present. And I do have that written down, but I want you guys to also listen. So if the mass of a molecule is an odd number, that means we have an odd number of nitrogens present. Any questions?
Yes, Rose. So the mass is the unfragmented molecule or the parent peak mass?
I'm so sorry. Say that one more time from the beginning.
So you said an odd mass number. Is that for the unfragmented or that's the parent peak, the M+ peak mass?
Okay. So those two are the same, basically, right? So the unfragmented means the M+. So that's essentially what the M+ stands for. So the M+ or the molecular ion or the parent peak, all of those things mean the same thing. And they are telling you the mass of the whole molecule. So the unfragmented molecule. So wherever your M+ peak is, you know that the corresponding mass is the mass of your total unfragmented molecule. And someone said, they kind of made a summary where it was fragmented equals base peak, unfragmented means M+. I don't necessarily want you to think like that because sometimes the most stable thing is the unfragmented thing. So in cases like this, when they're the same, all that means is that the most stable, so sorry, this was really bugging me that it wasn't even. The most stable possible thing is the one you already have. So that's a good way to answer this question, but in general, I don't want that to be the rule in your brain. All right. I don't know about you guys, but my brain is super tired. We got through it. We pushed through it. We finished mass spec. How are you guys feeling? Tired. Me too. Some people said better. Good. Okay. So someone asked about the odd mass. So let me clear that up. Just mass in general. If the molecule has an odd mass, that means an odd number of nitrogens. Also, before I let you guys go, let me do you a solid. Could you chill, please? Someone also asked about, okay, there's a bunch of questions, but it's a little overwhelming to do what I'm trying to find and also read that, so give me 1 second to get to your questions. First of all, I am required to send you this. So if you have not, please fill it out. Thank you very much. Next thing. Someone asked about the handout, and there was a couple comments about the handout. So the Chapter 11 handout will be up on Canvas. I thought I already uploaded it. I believe it just didn't, like I uploaded it, but you guys can't see it. So I'm going to go fix that right now. And it should be up very, very soon. I will send a little Canvas update when it is up, just so you guys know. All right. So today we covered a bunch of stuff. And there we go, mass spec. Shut up. Thank you so much. Okay. Bam. If you're confused about mass spec, watch this video. I explain everything in very much detail. Also, I absolutely love that by that one, like half a second, you knew that that was the intro. That's hilarious. So someone said I don't see anything. So here, let me send it one more time. Bam. So watch that video. It'll give you literally everything you need to know about mass spec. And if you have any questions on any other topics, watch the concept video for it. And yeah. All right. So will I be posting answers to the handout? No. Unfortunately, I will not, because I just honestly don't have time to make them nice and pretty. And then the follow-up question is always, well, just post the notes that you do at the end of class. I've noticed it causes problems with students, so I am not going to be posting it. I will try to send you guys like a cheat sheet before every exam, like after the, what's it called? Exam review, with just like the most important facts and whatever. So yeah, keep an eye out for that, but no answer sheet. I do apologize. However, if you notice, I always zoom out and allow you guys to take pictures and everything. I also do that so that if you're watching the YouTube video or like the session recording, you can go back and see all the answers. So that should be helpful. Okay, so someone said they feel a little bit better because they feel anxious when they just don't get it. I totally feel you. I totally feel you. It feels super overwhelming when you're just like in his lecture and then you just are like, I'm so lost. So that's why I try to explain it to you in a not super chemistry kind of way. Yes. All right. And the last thing that I saw is he going to ask questions? Is he going to ask questions like the ones at the bottom of page 6? Okay, let's look at the bottom of page 6. Yes, he is. He's going to ask questions like these. These are very good examples of how he might ask things. They're covered in the video, and also I will cover them in the exam review, but I do have to go, so I don't think we will have enough time to go through it now. I'm so glad you feel more confident. Hell yeah. Okay, I'm going to stop recording now.